Let's look at the ideal gas law and kinetic theory. First, we want to start with some background things. So things like molecular mass, the mole, Avogadro's number, things that you most likely know from chemistry class. So here we have the periodic table of elements, and there are all these numbers in here. We call this number up here the atomic number, and that stands for the number of protons that element has in its nucleus. So a hydrogen has 1 proton, magnesium has 12 protons, carbon has 6, and so on. Then the number down here is called the atomic mass, and it's measured in grams per mole, and that is what we want to concentrate on. That's what we want to look at. An atomic mass unit, U, was derived to be this value, and it was derived so that it is 1/12 of the mass of carbon-12, which is the most common, most abundant isotope of carbon. So this atomic mass unit was based on carbon, and if you think about it, since we're dividing this mass by 12, we essentially get roughly the mass of either a proton or a neutron in the nucleus of carbon. So then, to find the mass of one atom of any element, sodium, let's say, then you would have to multiply this value given here by the atomic mass unit, and then you have the mass of one atom of sodium. So here we have the atomic mass unit, U again, and then if we basically take 1 over that, we end up with Avogadro's number. I said basically because we would have to convert this into grams first. So Avogadro's number was defined as 1 gram mole, or simply mole, of a substance contains as many particles, either atoms or molecules, as there are atoms in 12 grams of the isotope carbon-12. And Avogadro's number then turned out to be 6.022 times 10 to the 23rd inverse mole. And like I said, this value and that are inverse of one another if this is in grams. So then the number of moles that were defined over here is the number of molecules of a sample divided by Avogadro's number. And if we multiply top and bottom of this by the mass of one particle, so we have basically just multiplying this quantity by 1, then mass particle times n gives us the mass of the sample, and mass particle of multiplied by the Avogadro's number gives us the mass per mole. So the number of moles can be expressed as the number of molecules divided by Avogadro's number, or the mass of the entire sample divided by the mass per mole. So then, combining these, we end up with the mass of the particle being equal to the mass per mole divided by Avogadro's number. So now let's look at the ideal gas law, and it's also something that you may be familiar with from chemistry. And the ideal gas law says that PV is nRT. Here, P is pressure, V is volume, N is the number of moles, T is temperature. If P is measured in pascals, SI units, volume is measured in cubic meters, again SI units, and T is measured in Kelvin, then R becomes 8.314 joules per mole, and that is known as the universal gas constant. So here is the ideal gas law in SI units, in which case R, the universal gas constant, has that value. Now, it's convenient to sometimes redefine some of the constants that we have, and in particular, Boltzmann defined this K, Boltzmann's constant is what we call it now, as the universal gas constant divided by Avogadro's number. When that happens, we get a new definition for the ideal gas law. So we get PV equals NKT, where N is the number of molecules. Here N was number of moles, K is Boltzmann's constant, and then we have the temperature. Now dividing R by Na gives us 1.38 times 10 to the negative 23rd joules per Kelvin. So this ideal gas law is an equation of state. What we mean by that is that a gas, if we measure its pressure, volume, and temperature at any point in time, then we pinpoint a state that the gas is in. It has a certain set of P, V, and T. But that gas can be moving from one state to another, so at a later time it has a different set of P, V, and T. So then if we rewrite PV equals nRT like this, so I isolated here things that are specific to the gas that don't change, like the number of moles and the universal gas constant, I end up with this constant for this particular gas being equal to pressure, volume divided by temperature. Now, as this gas is moving from one state to another, so one state with a specific set of PV and T, call them P1, V1, T1, to another state with a set P2, V2, and T2, this NR doesn't change. So that means that P1, V1 over T1 will equal P2, V2 over T2, all by setting NR equal to one another when we are dealing with different states. So now, three different physicists, people, came up with these laws that had nothing to do with the ideal gas law. They did not know the ideal gas law, but they tinkered with things in their backyards and figured out that if the temperature is kept constant, then P1 V1 equals P2 V2. Of course, we can now see why that is. If T is the same here, that means that P1 V1 equals P2 V2. Charles's law said that if the pressure is constant, then V1 over T1 is V2 over T2. And that makes sense now, once we know the ideal gas law. Same thing with Gay-Lussac. For constant volume, we end up with pressure over temperature equals pressure over temperature. So these equations will be very useful when we discuss thermodynamics. Now, let's look at the kinetic theory of gases. So let's say that we have a cubical box of side L that contains n particles. And the particles are really tiny compared to the walls of the box. And what these gas particles will do is just bounce around in here. Some go left to right, some go up and down, some go front to back. But we're wanting to look at the motion of these particles. Now, it is going to be easier if we just look at a single particle and see how that behaves. So here we have a single particle that bounces against this right wall and then bounces back. Now, since the wall is so much larger than the particle, we can assume that this type of collision is an elastic collision where the initial speed of the particle is going to be the same as the final speed. The directions are going to be opposite though. So that means that the force that this particle experiences as it's bouncing off this wall is the change in momentum, or the impulse, divided by the time. So the time that we have here is between successive collisions. So this particle may be bouncing against this wall, then back against this wall, and back against this wall again. So that means that the particle will travel twice the length of this box before it collides with the wall again. So then we can write that the average force that the particle experiences is the final momentum, so that is m times this v, minus initial momentum, m times v, divided by the time, which is, again, it goes back and forth between the two walls twice, so the time is 2L divided by v. So then when we calculate this, we have negative mv minus mv, that's minus 2mv, and get rid of the 2, simplify it over here, we end up with the average force being mv squared over L. But that force is the force on the particle. Now, so by Newton's third law, we know that there is an action-reaction pair for every force. So that means that there is this force on the particle that equals in magnitude and is opposite in direction to a force that the wall experiences due to the particle. So the magnitude is going to be mv squared over L, but the direction is going to be opposite. So opposite of negative would be positive. So here we have the average force on the wall, and that's mv squared over L. But this is only the force experienced by the wall due to one particle. We have n particles in the box. So we want to see what average force is exerted on the wall due to all of these particles. That force is going to be the number of particles divided by 3 times mv squared over L. There are a few things that we have to think about here. Why don't we just have n number of particles? Why is it n over 3? Well, because roughly a third of the particles move left to right, a third of the particles move up and down, and a third of the particles move front to back. And we're only considering the wall on the right here, so the average force exerted on this one wall then is going to be due to only a third of the particles that bounce against that wall. Now, not all of the particles travel at the same speed, so we're going to use this averaged v square, which is called the average value of the squared speed. Now, if we take the square root of this average value of the squared speed, we end up with something called the root mean square, or RMS speed of a particle. So we're going to be using this RMS speed quite a bit because that basically just averages all the different speeds that the particle can have, that all the different particles will have into just this VRMS. So then we rewrite the force as n over 3 mvrms squared divided by L. But now we want to know the pressure exerted on the wall as the particle all the particles bounce against this wall. So pressure by definition is force divided by area, and the area of this wall is going to be just L squared because we chose the object to be a cube. So then this becomes force, which is that value divided by L cubed, and it turns out that this L cubed is actually volume. So then pressure will be n over 3 mv squared over v, but we like this quantity. It reminds us of something. That something is kinetic energy. So it would be really convenient if we could put a 2 over here, and that would mean that to keep the ratio correct, we would multiply this by 2 over here and end up with PV equals 2 times n over 3 with times 1/2 mv squared, and that would be 2/3 the number of molecules times the average kinetic energy per molecule. But we know that PV is nkt. That's the ideal gas law where we use the Boltzmann's constant expression. And then since the left side of the equation is the same, that means that this side equals that side. So from that we end up with kinetic energy being 1/2 mv squared. We knew that before, but now it's going to be, we cancel the ends out here and we end up with 3/2 kT. So a very remarkable thing about this is that kinetic energy is only a function of temperature. So the kinetic energy of a gas is only a function of the temperature, and it's equal to 3/2 kT. Now, the reason we have a 3 here is because we're dealing with 3 dimensions. So we can say that there are 1/2 kT per degree of freedom of kinetic energy. Then we can solve for the VRMS from here and end up with VRMS being equal to square root of 3 kT divided by m. Now, one very important thing that we're going to be discussing in future lectures is total internal energy of a monatomic gas. And that internal energy is made up of a whole bunch of different types of energy. And one of them is the kinetic energy of the gas. There is no rotational kinetic energy because the particles are so tiny that any rotation gives them a moment of inertia of 0. And there are no vibrational forms of energy because those particles are not bound. We're just looking at a simple monatomic gas. So it turns out that this internal energy is just due to the kinetic energies of the particles. So then the internal energy of the monatomic gas is going to be n times for n particles that have a kinetic energy Ke, and that would be n times 3/2 kT. And if we substitute the K as R over Na, so then we have the Boltzmann's constant as the universal gas constant divided by Avogadro's number times T. And remember that N over Na is the number of moles, so I extracted N over Na here, and then I'm left with 3/2 RT. Then we end up with 3/2 nRT as the total internal energy of a monatomic gas. So the takeaway from here is that the kinetic energy of a monatomic gas is 3/2 kT, and the 3/2 comes from the fact that we're dealing with a three-dimensional model, so we have 1/2 kT of kinetic energy per degree of freedom. Then the RMS velocity is going to be 3 kT divided by m, square root of that, and the internal energy of an ideal monatomic gas is 3/2 nRT.